my name is Yashwant Panakonda, and today I'm going to present my BTech term project, which is about fair recommendation system using machine learning. So my objective of this BTP presentation is to create a fair recommendation system model, which is unbiased towards sensitive attributes, but performs well to recommend an entity to customer. My motivation behind the project is these days the recommendation systems are biased towards certain groups and attributes, resulting in an imbalance in power. For example, Compass, which is a recidivism prediction model, that is, it predicts if the criminals are again going to do any criminal activity. It showed biasness towards white, even though both white and African Americans have the similar chances. And another example is in job recommendation, where similar experienced candidates were biased based on their gender, if they're male or female. So in order to avoid bringing biasness, fairness in ML have gained significant attention. So I have learned about the recommendation system during my BTech term project. So a recommendation system is a subclass of information filtering system that seeks to predict the rating or preference a user would give to an item. It can be typically classified into three categories: content-based filtering, collaborative filtering, and hybrid systems. Out of this, collaborative filtering is the most common, which tries to predict a user's utility for an item based on other users' previous utility with the item. So the most commonly used datasets for recommendation models using machine learning are Movie Lens 1 million dataset, Amazon Book, Kovala, Yelp, and others. I have also studied about the fair recommendation system during my project. So it is a system. A system is considered fair when the recommendation is unbiased towards any group or individual, consumer, or even providers. Usually, a fair recommendation model gives recommendations by not taking into account certain sensitive attributes such as gender, age. So recently, researchers paid considerable attention to fairness issues for artificial intelligence applications, and it will be the center of attention in the future. So before going into the fair recommendation system, I tried to develop a name recommendation system using the approach of random walk. So here I built the movies graph with nodes as the movies and edges being the similarity between two movies. So I basically found out the similarity between two movies based on the genre and the year it was released. Now I start with the most rated movie as the first node, and we generate n random walks, each of length k. The random walk with the highest edge weight products was chosen to be the recommendation of movies for the user. So this was a very naive recommendation model that I built. And here are the results of my random walk recommendation system. So for checking the performance of my model, I use two metrics: hit rate and average reciprocal hit ratio. So hit rate is defined as the number of hits divided by the number of users, and ARHR is defined as the as 1 by number of users into summation of 1 by PI, where PI is the position of the ith hit. So here I have used Film Trust as my data set, and I have compared it with other models, other recommendation systems like Item KNN, Pure SVD, and so on. And I have set the best hyperparameters for my random walk recommendation system. And the best params were the number of random walks being 1,000 and the length of each random walk being 30. The hit rate I got was 0.184 and the IRHR I got was 0.027, which was very less compared to the other existing recommendation models in the world. So the disadvantages of my random walk recommendation system were it was based on random probability and could not ensure to provide the best recommended items, and that too fair. Also, the selection of the starting node must be of the highest rating provided by user, and which is not certain. And there is no type of learning about the user in the model, and therefore it is a very naive model which recommends random items to the user. So I tried to study other collaborative filtering recommendation models of machine learning, which basically used concepts of graph neural networks. So I understood what the graph neural network was. It is a type of neural network which directly operates on the graph structure, where every node in the graph is associated with a label, and we want to predict the label of the nodes without the ground truth node. So basically, a GNN generates embeddings while taking into account the graph structure, and it utilizes the embeddings of the central node's neighbors to update the central node's embedding. So this allows the GNN to create similar embeddings for the nodes that are more closely related from both a local and relatively a global perspective. Now, this is how a GNN works. We basically give an input graph through certain GNN blocks, the output being a transform graph, which when passed to a classification layer gives prediction. This prediction can be for the node, the edge, or the global predictions. So in a GNN layer, we try to get this d-dimensional vector, which contains the information of a node V neighborhood, which is done by using a function which takes in the features of the node, uh, the features of the edges connected to the node, and the embedding of the neighboring nodes of node V, and the features of the neighboring nodes of node V. Then at each layer of the GNN, we do the message passing or the neighborhood aggregation for each node, which is defined by the function ht plus 1 equal to f into ht comma x. Then once we get the output from the GNN, we can pass it into an output function g, where we pass our d-dimensional vector and the feature vector to get the output for the user and item. Now for training this GNN, we use the loss function given here, which can be optimized via gradient descent. And also in different variants of GNNs, multi-layer perceptrons are used to better understand the model. Next, I have gone through understanding a much higher performance variant of GNN, which is light GCN. And it delivers state-of-art empirical performance on benchmarks for recommendations, including Govala, Yelp 2018, and Amazon Book dataset. So this is how the light GCN architecture works. So initially, we give a user and item embeddings of dimension D, and in each layer of the light GCN, we compute its updated embedding as the weighted sum of embeddings from all its neighboring items. So for the user, we take weighted sum of items, and for the item, we take the weighted sum of embeddings of the user. And we iteratively do it for k times, meaning we derive the kth layer embeddings ek. Next, the second step is the interlayer combination, where once we obtain the embeddings of all the k layers, we use the weighted sum to calculate the final embedding of the user and item. Now, the why the inner product of this user and the item embedding is going to give the similarity between the user and movie, which tells us how better we can recommend the item to the user. Now, for training this light GCN, we use the Bayesian personalized ranking loss function for training, which also takes into account the L2 regularization for the initial node embeddings given to the light GCN. Next, I have also gone through the hyperbolic graph convolutional network, and this is one of the best performing recommendation system due to the use of hyperbolic geometry. This is because in particular it is good for scale-free graphs. So scale-free graphs have tree-like structure, and in such graphs, the graph volume defined as the number of nodes within some radius to a center node grows exponentially as a function of radius. This GNN involves doing feature transformation and neighbor aggregation in hyperbolic space instead of the conventional Euclidean space. So here we project the Euclidean embeddings into the hyperbolic embeddings by the use of mapping. So here we use exponential and logarithm mappings. So exponential mapping is used to transform the embeddings from the tangential space onto the hyperbolic space, while the logarithm maps are used to transform from the hyperbolic space to the tangential space. So we can find the tangential space and the hyperbolic space using the Minkowski inner product, which is defined as follows. And the norm of a point on this is defined as the root over the Minkowski of the inner product. So in an HGCN, the first step we do is mapping the Euclidean embeddings to the hyperbolic embeddings. So this is done by the formula given here. Then we transform the features onto the hyperbolic space, which is given by multiplying the weight matrix with the hyperbolic embedding using the exponential map. And then the third step, we do the neighborhood aggregation on the hyperbola and manifold. So here we can find the weight using the softmax applied on the multi-layer perceptron of the logarithmic maps of the hyperbolic embeddings. Then we aggregate all of these embeddings onto the exponential map, and then we apply a nonlinear function onto it to give us the output. So this is how our Euclidean GCN architecture looks. And this, when converted into the hyperbolic geometry, this looks like this, where the nonlinear activation is conducted on different curvatures. And after going through the hyperbolic graph convolution network, I have gone through a fair recommendation system model using machine learning, which is known as the FAIRGO model. So here, by defining a sensitive feature set like gender, age, etc., the model takes the user and item embeddings from the recommendation models as input. Here they have taken embeddings from the GCN, where it learns a filter space such to obfuscate any sensitive information in the sensitive attribute set while simultaneously maintaining the recommendation accuracy. Specifically, it learns a composition of each sensitive attribute filter that transforms each user's and item's original embeddings into a filtered embedding space. As each user can be represented as an egocentric graph structure, the filters are learned under a graph-based adversarial training process. Here, each discriminator tries to predict the corresponding attribute, and the filters are trained to eliminate any sensitive information that may be exposed by the user-centric graph. So here is the how the Fairgo recommendation model works. So here we have the original embedding matrix C, which contains the embeddings of users and items, and we have the egocentric network for a user. Then we projected onto the original embedding space. And if we consider K sensitive features, then we build K filters. These K filters are used to map the original embedding vectors onto the filtered embedding space. And these filtered embedding space embeddings can be multiplied together to get the predicted preference of the user U to the item B. But in order to train this filter network, we use K discriminators, which in turn learn adversarially to find the best fit, such that no sensitive attribute is found out in the training process. So here, the filter network and the discriminator network play the following two-player minimax game with the following value function given as V, filters and the discriminator, which is given by VR minus lambda VG. So here VR refers to the log likelihood of the rating distribution. VG refers to the log likelihood of the predicted attribute. And lambda here is the balance parameter. So if lambda is set to 0, then there is no fairness. And these are all the math which is going behind the Fairgo recommendation model. So also I have studied about the results of the Fairgo recommendation on the GCN embeddings. So as you can see, the Fairgo recommendation model was performed on different embeddings coming from PMF, that is positive matrix factorization and graph convolutional network. So taking into consideration the gender, age, occupation, and all the combined set of attributes together, we see that the Fairco GCN performs better and it is unable to predict the sensitive attributes. As we can see, the AUC score before Fairgo and after Fairgo has significantly decreased for these sensitive attributes. So to summarize my work up till now was I have understood about the recommendation systems and the need of fair recommendation models in real world. I've built a name recommendation model from scratch to understand about recommendation of items using random walk approach. I have studied on the importance of collaborative filtering in recommendation systems and started exploring high performance recommendation models. So these were based on graph neural networks, which are highly used in recommendation models. So I have also studied improvised GNN recommendation models of light GCN and HGCN and ran the code of the models to understand how they perform. I also studied about the fair recommendation model FAIRGO as to how it provides fairness in recommending items from certain sensitive attributes. So in the future, my aim for this project will be to build a fair recommendation system which gives a better performance in recommendation as well as keeping the fairness of the recommendations. So the possible approaches that I will be using in the coming semester would be the combination of light GCN with FAIRGO and the combination of HGCN with FAIRGO. So my first approach of combination of light GCN with FAIRGO is to include the light GCN embeddings instead of the original embedding matrix key from the GCN. This would actually be better in performing for the recommendation as well as the fairness for the recommendation model. So I'm going to try this in the coming semester. And then I'm also going to try uh, the combination of hyperbolic graph convolution network with FAIRGO. So here, I'll be using the hyperbolic embedding matrix scheme, and the original embedding space and the filtered embedding space will be transformed onto the hyperbolic space. So here the discriminators and the filters, they both learn on the hyperbolic space. So this will actually help improve the performance of the recommendation in the future, and also it is going to increase the fairness of the recommendation system. So I'm hopefully trying to bring in these approaches in the next semester for my BTP term project. So this was all it. Thank you so much.